Today, we're diving into a really cool breakthrough that's changing how we design pretty much all the complex electronics that power our lives. It's a story about a major roadblock in innovation and, a pretty genius way to get around it.
So, let's set the stage. Our world is going electric. And I mean, it's happening fast. Think about it. Electric vehicles, renewable energy, even all-electric ships and planes. They all run on these really sophisticated direct current, or DC, power systems. But just look at a diagram like this. These things are incredibly complex. Making sure they're safe and reliable, that's a huge, huge challenge for engineers.
And that right there, that's the central challenge we're facing in this new electric age. How on earth do you design these incredibly intricate systems without things going haywire?
Well, the answer is simulation. I mean, you can't just build a multi-million-dollar power grid for a new electric airplane and, just hope for the best. No way. You have to build a digital twin first, a perfect virtual model where you can test everything, every possible surge, every little interaction to make absolutely sure it's going to work in the real world. But here's the catch. This is where the problem really starts. Simulation is absolutely essential. But what happens when the very tools you need to innovate are actually the biggest things slowing you down?
So let's talk about this simulation bottleneck. For years, engineers have basically been stuck between a rock and a hard place.
On one hand, you've got what we can call the brute force method. It's like the tortoise in the race. It simulates a system millisecond by millisecond. It is incredibly accurate, but oh my gosh, it can take forever and costs a fortune in computing power. Then you have the shortcut methods, the hare. They're way faster, but they cut corners. They simplify things, and they often miss all the complex electrical noise. The technical term is harmonics that can actually cause huge problems.
And hey, don't just take my word for it. The researchers in the paper we're looking at today say it plain as day. The super detailed simulations just gobble up time and memory, while the simpler way is just, they aren't accurate enough. It's this classic, frustrating trade-off between speed and accuracy, and it's a real drag on innovation.
So you have to ask, right, do we really have to choose one or the other? Is there some way to get the best of both worlds, to have a method that's both super fast and perfectly accurate?
Well, it turns out the answer is yes. And this is where a truly elegant solution comes into play, a harmonic breakthrough that completely changes the game.
It's a method called harmonic state space, or HSS for short. Now, instead of looking at tiny, tiny slices of time, HSS does something different. It looks at a system's electrical signals as a collection of different frequencies, or harmonics. A good way to think about it is like all the different musical notes that make up a single chord. HSS analyzes how all those notes interact at the exact same time.
And this is a fantastic analogy. Think about analyzing a song. The old-school simulation method is like listening to it 1 millisecond at a time. Yeah, it's detailed, but it would take you forever to actually understand the whole song. HSS, on the other hand, is like someone just handing you the complete musical score. You instantly see all the notes, all the harmonics, and how they all fit together. You get the full picture almost instantly. And here's how it works in practice, which is just brilliant. HSS lets you create these standardized digital building blocks for every single part of a system. A power converter, a cable, you name it. Then, engineers can just take these pre-built, pre-analyzed blocks and snap them together like Legos. You can build a model of a massive, complex system in no time.
Okay, so the theory sounds amazing, right? But does it actually hold up in the real world? Let's check out how this new method stacks up against the old gold standard.
And here is the proof right here. Look at this graph. The red line is that slow, super detailed traditional simulation. The blue dashed line, that's our new HSS method. They tested a system startup, and look at that. They are a perfect match. HSS gets the exact same results.
All right, but what about when things get a little chaotic? The researchers threw a curveball, a sudden power surge in the system. And again, check it out. The HSS model in blue perfectly tracks the traditional model in red, so it's just as accurate even when things are changing fast.
Now this is really cool. The precision is actually tunable. On the left, you've got a simulation using just the basic frequency. It's kind of like hearing only the main melody of a song. But on the right, when the model includes more of those harmonics, more of the musical notes, the simulation becomes crystal clear. It's a near perfect match for reality. So engineers can literally dial in the exact level of detail they need for the job.
So we've established it gives you identical accuracy. But what about the speed? This is where it gets
absolutely nuts. The researchers found that HSS can slash calculation times by over 90%. That's not just a small improvement. That is a revolutionary leap forward.
And a leap like that, well, it has enormous consequences. Let's zoom out and look at what this really means for the bigger picture of technology and innovation.
At the end of the day, HSS finally solves that fundamental problem, that trade-off that's been holding engineers back for so long. It delivers the holy grail of simulation. You get the pinpoint accuracy of the slowest methods, but with incredible speed. So why does this matter to you and me? Well, it means engineers can design and test new technology way, way faster than before. This leads directly to more reliable power grids, more efficient gadgets in our homes, and fundamentally safer designs for electric cars, ships, and airplanes. It literally speeds up the pace of innovation for the entire renewable energy sector.
By just completely rethinking the problem, by looking at the whole musical score instead of listening note by note, this method broke down a massive barrier. It really makes you wonder, as our world keeps getting more and more complex, what's going to be the next big idea that powers our future?